Welcome back. This is a continuation of the previous lecture, and here we will start with the multimode digital current mode control, and we have already discussed digital multimode control consisting of PWM and PFM, and we have also discussed about the module instantiation. Okay. Now, we are going to talk about what is the modulator selection. Okay. So, first the modulator selection, it takes the clock, highest frequency clock input, because this is to generate the timing circuit inside the modulator that we are going to discuss. It also takes the PWM signal, because if you remember in adaptive on time, which we have discussed in lecture number 19, this PWM clock was used, that 5 microsecond time period was like an external clock which is coming periodically. It will check whether your comparator output is high, but on time is still not activated, or your off time is elapsed. So, all this activity is checked, because then it may initiate another constant on time action. Okay. Then it also require a reset, then QTR, and this is a flag signal which will decide whether it is a constant on time or whether it is a PWM or PFM. This is a minimum time, because every constant on time should have a minimum of time. This is a comment, and the output of this block is Q. That means, I would say this block has modulator selection, it has this F clock, high frequency clock, then it also take F PWM, then it also have a reset clock, then it takes QTR, that is coming from voltage comparator, it has a select line F PWM PFM which controller, then it also has the minimum of time, that is a vector quantity, and its output is Q out. Okay. Now, the first thing, if you remember, this circuit, we have this block. If you remember, this is the set and so this is set reset. What is set? It is coming an enabling signal, and we will discuss how to generate this enable signal, and this is a reset pulse. Typically, it should come from, that means, I am telling that in PWM, it is okay. So, there are two functions here. One feature, this modulator will also have PWM, right. So, under PWM, it will take a reset set pulse. Set, it will have a switching frequency clock which is F PWM. At this edge, this will turn on, this will Q, and we call it as a Q PWM. And this is coming from comparator. And what is the comparator? We have that DAC, this is your I peak, this is Vp in voltage sense, minus this is Vsn. So, this is your comparator output. Okay, directly coming. So, this will generate the PWM clock. Next, for the constant adaptive on time modulator, and this we have discussed adaptive on time. That means, now for adaptive on time, we are using a clock synchronization. If you remember that the actual comparator output, which is V peak minus and Vsn plus, this is the comp. This, if you give it to the adaptive on time, and we saw lecture number 100, that it has to drive multiple signal inside the modulator, and it was getting loaded. So, to avoid this loading effect, we made it clock synchronized. That means, this is the input, it can be a D flip flop, you can say a D flip flop, and this is a high frequency clock, and this is, we call it as a here, that this pulse we are internally defined as a reset, and here it is called a reset sync. This is internally clock name as reset. That is why we are calling as a reset pulse. It is equal to reset sync when that clock edge come, this clock edge come. Now we are entering into adaptive on time modulator, and any adaptive on time modulator we have discussed in lecture number 100, that if you go lecture number 100, what was needed? Sorry, lecture number 96 also we have discussed that constant on time modulator require an enable pulse, right. So, enable and high frequency timer circuit like a N, I would say on time, N mean time. This is a regular constant on time. But what was the case? And it consists of two. That means the first block will be monoshot constant on timer. This we have discussed in lecture number 96 in detail, followed by minimum of time, and this will generate your Q. So, this will require enable signal and this clock, this F clock, high frequency clock. But in case of adaptive on time, this part is coming from the adaptive, that means your current loop. Okay. So, that is why adaptive on time modulator, which we have discussed in lecture number 100, adaptive on time. So, I am not going to discuss again in detail adaptive on time modulator. Okay. So, adaptive on time modulator we have discussed in lecture number 100. So, one can refer how to generate, everything else is same. Here adaptive on time we are using, they are also use a peak current based approach. So, everything is same, it is details are there in lecture number 100. I am not going to repeat. And the output of the adaptive, and we know for any adaptive on timer, again in lecture number, I think both 96 and lecture number 100, we have discussed that any constant on time modulator or adaptive on time modulator require a clock manager circuit, which will generate the enable clock. It ultimately generate to, this is to be output, and that will be the input to the adaptive on time modulator, or you can say constant on time modulator, and the Q tier is the input. So, this also have an input external clock, this clock, these are the input, and we know that this generate a trigger, it will generate a positive edge trigger for the Q tier, which is the output of the voltage comparator. That means, if you take output voltage and Vref, if the output voltage falls below, that means reference, that means if this is greater, then this is your Q tier. This is for analog comparator, but since we do not have analog comparator, we are using the ADC 20 megahertz clock ADC virtually like analog comparator by particularly comparing that output of the ADC with the reference voltage, but this can be replaced by an analog comparator. So, we are detecting this edge, then we are generating the minimum clock, that means when the on time is over, then it will have a minimum of time, after that there will be a flag and it will check whether Q tier is still high, or external clock come whether Q tier is high, and this external clock we are talking about a PWM clock. Sometimes this constant on time you have to synchronize with the external clock also, we have discussed. So, this edge trigger we have discussed in lecture 96, edge detection circuit. Edge detection circuit we have discussed also lecture number 96, and the dead time circuit, here we have option. So, for the PWM clock, dead time circuit is just simply you have a Q in, then this dead time circuit, it generates two signal QH, QL, this is the local variable. And finally, what is the actual signal going into this? You see QH temp, this is the output of dead time circuit. The outputs, this is one, another is Q low temp, the high side and low side, and this was the dead time circuit which was generating dead time circuit. What was the input? It was Q in, and that we have defined as a Q PWM. It is basically the Q PWM is the input. Okay. Now, when the PWM will come, again it will take two paths. Q PFM 0, 1, this will be your Q high side gate signal, and this is again a PWM PFM. This will come as this 0, 1, and this will be simply 0. This will go to the Q low, the gate signal, and this is the logic. So, now we are going to show FPGA prototyping and hardware implementation of peak current base mode mixed signal PWM PFM multi-mode control. So, this is the block that we have to synthesize in Verilog, we have discussed. Now, we want to show the hardware result, and we are using our hardware prototype 1.8 microhenry inductor, 200 microfarad capacitor. We are going to test at 3.3 volt input, but user can use different specification, and we are using 1 volt output. Switching frequency is varying for PFM, but it will be fixed for PWM, which is 200 kilohertz, and load resistance we are changing from 13.5, because we know there are two load resistance RC, this RC is this, and there is another load resistance RSW, which is 0.33 ohm, and this whenever the Q load is high. Okay, that we did. Controller gain, we are using the PI controller gain same that we have used in lecture number I think 107 and 08, and current sensor gain all are known, voltage feedback gain this much, ADC resolution is 12 bit, DAC resolution ADC resolution 10 bit and DAC resolution 12 bit with offset binary, we have discussed. Now, we are going to show experimental case study. At 3.3 volt input, 1 volt output, we are changing a load resistance from 13.5, which was the continuous load, and we are changing to 0.322 when both the resistance are connected together, and it shows the load transient performance. This is the step up transient, step down transient when it is throughout PWM, digital current mode control. Now, we are enabling multi-mode control. So, when you say multi-mode, you see there is an additional thing, because integral we are starting with 0 resetting, and that time as we discuss in I think lecture number 114, that the error will be, because in PFM generally output voltage is above the reference voltage, and as a result our error voltage will be negative, and this is going negative direction. Another thing, during step down transient we are enabling this PWM operation for certain time, that is how we can reduce the settling, improve the settling time, and we can retain the same settling time for PWM. And you can see during light load it is in adaptive PFM, peak current base. Okay. And this is the transient performance comparison. This is throughout PWM, and this is a multi-mode control. So, there will be reduction because of this negative error at the time of transition when we are making integral reset, but there are research paper and commercial product which try to improve this mode transition. This penalty is due to the mode transition when you are doing integral reset. So, there are n number of technique to detect transient and take action by a nonlinear adding nonlinear term. So, we are not going to discuss here. This may be a research topic, or the participant can do further exploration. So, in summary, we have discussed top down design methodology of mixed signal peak current based PWM PFM control. We have synthesized this control technique using Verilog programming, and we have shown experimental load transient performance along with a comparative study with throughout PWM and a multimode control. That is it for today. Thank you very much.